what I would like to do is take one very important result of Castelnuovo, the so-called criterion of rationality, and explain a little bit its origin and the developments which have been afterwards. So the story starts in 1875 with a very short paper by Lueroth, a 2 pages paper by a German mathematician, Alfred Lueroth. He takes a curve, any curve, in plane curve defined by polynomial, and you assume that it can be parametrized by rational functions. So xt, yt are a rational function of t, and we can describe a general point of C by this parametrization. Then we can find another parametrization with a different parameter u, such that the correspondence between the parameter and the point on the curve is essentially one-to-one, except with finitely many exceptions. So that's Lueroth's theorem. In other words, we assume that we have a rational map from the complex number to the curve. So it's rational because there can be some poles here on x, y, so there are some values of the parameter for which the map is not really defined. And dominant just means that the general point of the curve will be attained by this map. And so the assumption is that we have such a map, and this implies, Lueroth's theorem tells us that there exists a birational map, so that we have a different map, which is essentially one-to-one with finitely many exceptions. Okay, here is an example that probably everybody knows. This goes back to the Greek mathematicians. It's called the strophoid. I take this equation, x cubed minus y cubed for xy, and you can parametrize it, for instance. If you take these values for x and y of t, then you can check that this indeed satisfies the equation. This is not one-to-one because t and minus t give the same point of the curve, but of course, in that case, the solution is obvious. You just take t squared as the parameter, and now you find a parametrization which is one-to-one, essentially one-to-one. For instance, here, u should be different from 1, because otherwise you go to infinity. Okay, so that's Lueroth's theorem. 2 words about the proof. Lueroth uses, it's a very short paper, and uses a sort of very ingenious algebraic argument. Now you find the proof of Lueroth's theorem in any book on Riemann surfaces, really at the beginning. This is a modern proof. What you do is that you compactify C. You had one point at infinity, so now it's a projective line over C, or if you prefer the Riemann sphere. You do the same with C, taking out the singular point. So reg here means that you take only the smooth points of the curve. For instance, in my picture here, I will take out this. This is a double point here, so I will take this out. And then, again, Riemann tells us that this embeds into a compact Riemann surface, C bar. And now our rational map here automatically extends as a everywhere defined map, holomorphic map, from P1 to C bar. This is essentially a Riemann extension theorem. Now, so we have these compact Riemann surfaces. Suppose we have a holomorphic one form on C bar. So one form is something you can write locally as f of z dz. This is the usual notion. With a different f. F is not a good notation here. So g of z dz would be better. Then you pull back the form, and by standard result, this is again a holomorphic one form now upstairs on this P1 here. So you can always pull back form. So you get holomorphic 1/4 on P1, but I mean, it's well known since Riemann that such a form does not exist. It should be 0. This implies f upper star omega is 0, and standard argument, this implies in fact that omega itself is 0. There is no holomorphic, there cannot be any holomorphic one form on our curve C bar. And again by Riemann theory, this implies C bar isomorphic to P1. So this is the modern proof. I must say I find puzzling. I mean, this probably illustrates what Gabi was telling yesterday, that Riemann's idea to some time, you really needed some time. I mean, Riemann's works appeared in 57, we are in 75, 18 years later, and Lueroth doesn't mention at all the idea of Riemann surfaces. This is strange for me because Lueroth was essentially almost, not formally, but informally a student of Clebsch. Clebsch had translated Riemann's work in algebraic terms. In particular, he had noticed that a curve of genus 0 is rational. So it's strange for me, but anyway. In any case, I mean, I think this paper of Lueroth made a strong impression on the mathematician of the time. And later, so we are now essentially in the decade 1890, 1900, Castelnuovo and then Regress build the theory of algebraic surfaces. Here they are. I mean, we have seen the pictures already many times. And you could say that starting from a primitive stage, I mean, there was essentially some work by Max Dutter, but I mean, a few comptes notes, it was really not much. They obtained in a few years really essentially an almost complete classification of algebraic surfaces. This is a wonderful work which was done in maybe in something like 10 years or something like that. As I think Enrico already mentioned, they were very young. Let's say in 1895, I mean, Castelnuovo was 30, and Request was 24. I mean, it's quite remarkable how these people worked at this age. Anyway, one of the first questions that Castelnuovo attacked was to extend the Lueroth theorem for surfaces. So the question is, we have an algebraic surface, we have a rational dominant map from C to S, so it means that we can parametrize our surface by rational functions, exactly as in our case. Does that imply that we have a birational map? We have a one-to-one parametrization, and the answer is yes, and this is Castelnuovo theorem. In modern terms, or not so modern, but a little later, this property here is called unirational. We said that the variety is unirational when it is dominated by some projective space or linear space. And this is rational, so unirational implies rational for surfaces. I won't discuss the first proof of Castelnuovo, which used a lot of surface theory, but then he tried to imitate the proof of Lueroth theorem, at least the proof I gave using Riemann surfaces. So it is to find a numerical criterion characterizing rational surfaces. Certainly, if S is unirational, I mean, the same argument tells you that S cannot have any holomorphic forms, one form or two forms. So one form is something which is written like this in local coordinates x, y, or two form would be something written like this. For some time, okay, maybe I should I put a footnote here. I am actually cheating a little bit. I'm making an anachronism. Castelnuovo would not consider one form. I mean, he would use the equivalent vanishing of the so-called geometric and numerical genera. It's a little more complicated to explain, so I prefer to switch to the modern formulation. The equivalence was proved by Poincaré a little later. But let's put it this way. And at first, Castelnuovo tried to prove that this punishing of four holomorphic forms characterizes rational surfaces. But he had a problem, he could not eliminate, I mean, he did a lot of work, I mean, but there was still one possible type of surfaces which possibly could exist, not rational, but having no holomorphic forms. He discussed this with Enriquez, and Enriquez found indeed a non-rational surface of this type, which we now call the Enriquez surface. And this is the letter from Enriquez to Castelnuovo. He said, look there, if maybe you could find a surface of degree 6 having double, being double along the 6 edges of the tetrahedron, if it exists. And in fact, it exists, and this is the famous Enriquez surface, which is certainly important in the Enriquez classification. Here it is. So this is a big little film of the Enriquez surface. You see very well the tetrahedron here, and the surface is there. Okay, so what? So in Castelnuovo found the correct characterization. Again, I put it in modern terms, as rational if and only if there is no holomorphic one form as before, but we need no quadratic two forms. It's in something which can be written locally as dx with dy squared. I can't give the details, but this is essentially. And from this, you get immediately the Lueroth result. I mean, the fact that the surface is rational, because again, if a surface is dominated by P2, then you cannot have any non-zero one form or quadratic two form. So a unirational surface has this property, hence it is rational. This is quite, first of all, this is a major step in the classification of surfaces. And even today, I mean, it's still a difficult theorem. I mean, there is no very simple proof of the result. It's a deep result. Okay, of course, when you see that, I mean, what's for curves, what's for surfaces, I mean, you cannot resist to ask yourself what happens in higher dimension. So, do we have still this implication in dimension 3 or greater than 3? So, certainly, people looked at that. I mean, in the introduction of this paper, and Lueroth said many people have tried, but I don't have any other proof of this claim. Anyway, in 1912, Enriquez published again a very short paper, 3 pages, claiming to give a counterexample. You take just in 5 space, in C5 or P5, a 3-fold given by 2 general equations, one of degree 2 and one of degree 3. Actually, what Enriquez does in this paper is to prove that they are irrational with a very clever and correct argument, and he relies on an earlier paper of Fano from 1908 for the non-rationality. Here's a picture of Gino Fano, who was born the same day as Enriquez, by the way. Coincidence. So, unfortunately, the Fano's analysis is incomplete. The problem is that the geometry in dimension 3 becomes, the rational geometry in particular, becomes much more complicated than for surfaces. And the methods of Italian geometers were insufficient to treat all cases. Fano made other attempts, one in 1915 and one much later in 1947, where in the last one he claims that the general cubic threefold in 4 space is not rational. It was a long-standing conjecture. It's mentioned several times by classical geometry. I don't know exactly who first asked the question, but it's a recurrent question at this time. But again, I mean, this is certainly not acceptable by modern standards. I have tried to make some research on how this was perceived by the Italian geometers. I've never seen any criticism of Educa's paper. So here are some, for instance, Castelnuovo gave a general talk in the ICM at Bologna about the Italian algebraic geometry, and he cites this result as one of the highlights of Italian algebraic geometry, and Severin and all these guys do not apparently question the validity of the result. Criticism appears in 1955 in the book by Lueroth. There was a small school of English mathematicians, all students of Henry Baker, with Roth, Sample, Beauville, and Guido, and all these, and who continued in the tradition of Italian algebraic geometry, but perhaps with a little more criticism. And in his book, I mean, this is one of the first Springer book that is the Grundlehre or something like that. And so it's widely available in libraries. It's a very nice book. And so he made a detailed analysis of Arnaud's attempted proofs, and he concludes that none of this can be considered as correct. The amusing detail is that he continues to give a counterexample, which is interesting. Actually, he takes an request construction of the request surface. And so, now we take a threefold of degree 6 with double, which is double along the how do you say, facets of whatever it is, simplex in for space. And he claims, he shows that it is irrational and not simply connected. Hence it cannot be rational because a rational smooth projective variety is simply connected. That's easy to see. The merit of this example that it gave rise to a paper by Serre in 4 years later, so I think it's 1959, where he showed that unirational variety is always simply connected. So Ross was again wrong. And then the problem was again open till we arrive now to the modern era, where new extremely powerful methods were introduced, shift, basically in cohomology, and it was a real revolution in algebraic geometry, essentially led first by Serre and then by Grothendieck. At first, the development was very abstract, and Grothendieck had a very abstract mind, and was oriented towards arithmetic aspects. But later appeared a trend to use this method to revisit classical problems, particularly in the US with Mumford and Griffith, and also in the Soviet Union with Shafarevich and Manin. And again, a new coincidence. In 1971 appeared almost simultaneously 3 papers with 3 very beautiful examples of unirational, non-rational varieties. So let me give the authors, the example, and the method. So Clement Griffith proved the old conjecture that the cubic in P4, technically it's just a smooth cubic, or think of a general cubic in P4, is indeed not rational. It was known for very long that it's unirational, Then the method was using Hodge theory and the so-called intermediate Jacobian. Then Iskowski and Manin proved that, to be precise, it proved that every quartic, every smooth quartic hypersurface in P4 is not rational. And Beniamino Segre had proved, not so long before, that some of these quartics are unirational. So again, this gives a counterexample to the Lueroth problem. And what they did basically is to take one of Fano's ideas and to realize it in a completely correct way. I mean, it's a non-trivial paper, highly non-trivial paper, but it works. Finally, the third example, maybe I will come back to this, it's due to Artin and Mumford. I'll put a specific example, I will say more in a few more. And the method is basically algebraic. I mean, they use essentially what is called the Brouwer group of the variety. So we had this, not only we had 3 examples, but we had really 3 different methods and quite efficient to prove results about non-rationality. So these 3 papers has been extremely influential, and thanks to the method they introduce, many examples have been worked out, essentially in dimension 3. I will come back to that. We can say they are still essentially the only method known to prove non-rationality. This is not. I should mention that there has been later also a nice result by a nice construction by Collard, but again applying only to some specific varieties. An interesting fact is that the 3 methods, first of all, are completely different. I mean, they use very different methods, and also they apply to different kinds of varieties. So together they cover quite a lot of objects. But as I said, for instance, I mean, if you put essentially the 2 first methods together, you get really many examples in dimension 3. Actually, all natural examples, hypersurfaces of low degree, and you can decide using one or the other method, you can decide whether they are rational or not. And most of them are actually not rational. I mean, those who were known to be unirational are in fact not non-rational. So this gives really a lot of examples, but in dimension 3. Only the Artin-Mumford method, and they give example in dimension greater than 3, but they are quite particular because they are from the particular threefold, certain double covering of a P3 branch along a singular quartic times Cn is not rational. So the situation improved last year, maybe it's 2 years ago now, it depends if the paper has not yet appeared, but preprint I think appeared 2 years ago, with a very nice idea of Claire Voisin, who improved the method to obtain new results. So here is a theorem. You take a surface defined like this. So you can think of this as being a double cover of C3 or P3 branch along a general quartic hypersurface. So you take for F a general degree 4 polynomial, and this variety is unirational, that was done much before, but it's never, any product V times Cn is not rational. So it's not what is called stably rational. So the difference with Artin-Mumford result is that in the case of Artin-Mumford, this F here, or this V, was very particular, while in fact the result holds true for all general polynomials. So interestingly, our new idea is to use something maybe unfortunately called the Chow group of zero cycles, which is in fact something which has been studied for 20 years by Severi. Now, her method again is quite general. I mean, it gives a lot of new examples of unirational varieties, which are not rational, but even when you take the product with some rational variety, it doesn't become rational, so they are not stably rational. And here are some examples. So, using an improvement on our method, I proved that you can do the same with 5 or 6 variables. I mean, with a variety of dimensions. This is a variety of dimension 4, this is a variety of dimension 5. This is a general double covering branch along a quartic. And this is not rational and not even stably rational. I think this is the first example in dimension greater than 3, which is not a product, I mean, which is really a prime, what is called a prime phenomenon. Another example is a variety, now again of dimension 3, but defined by 3 general quadratic equations. This follows from a very recent result of these people here. I mean, their result is much more general. I just took one application of the result, but they give a lot of examples. There are other examples, again using particular by Guido and Lueroth, using this idea of Kerr-Voisin. So this is really a new advance in the subject. Okay. Conclusion. When did I start?
Quarter to little bit, half an hour ago. Half an hour ago.
No, I went too fast. Sorry, nobody will complain. Okay. In conclusion, I mean, this is still a very active subject with many open problems. Let me just conclude with one famous example. For a long time, it was this conjecture that the general cubic threefold is not rational. This was proved by Clemens and Griffiths. But you can ask in general, for higher dimension, what is the situation? And this is completely unknown. The conjecture is that the general cubic hypersurface of dimension at is 4 is not rational. There have been many attempts recently and many interesting possible attacks of this problem, but I think this is still wide open. The difference is that in that case there are particular, for instance, for fourfold or in general in any even dimension, there are examples of cubic hypersurfaces which are rational. So it's a slightly different situation of the three-dimensional situation where they are all not rational. Okay, I think I will stop here.
Thank you very much for this talk. Questions? Remarks? Gabi.
So what was the Lueroth proof, the manipulation, the original proof? Is it instructive?
You mean Lueroth?
Yeah.
It's algebraic. It's
Yes.
I don't know if it
Actually gives an algorithm. It gives contrary to the case, to the two-dimensional case, it gives an algorithm.
Yeah.
It gives an algorithm.
How to found the
So you give a
parameters?
parametrization.
Also, you really
describe
you write down your xt and yt as rational functions, and you eliminate the denominator. So you have two equations, and you reduce somehow. I mean, and there are some clever arguments to say that you can get down till this injectivity statement. It's completely algebraic. I think it works over any field actually.
Any field.
Yeah, you don't. Of course, it does it over C, but it works over any field. Contrary to the case of surfaces.
So I think it's still a problem to find an algorithm, right? Given a parametrization, a rational parametrization of the surface to get a birational.
This I don't know.
I think this
This is probably difficult.
is tricky.
Yeah,
Yes.
I'm sure.
Okay, if there is no other question or remark, let's thank Arnaud again.